Welcome. In this video, we'll be talking about distributed file systems. So, what are distributed file systems? These are file systems that have files or parts of files that are distributed across multiple file servers. So, here we have an example of a file system where an application using a file system client uses a network protocol to access files across multiple file system servers that may have multiple files. Now, even though the files are scattered across multiple servers, the client has a single view of the file system namespace. So all clients see a single global namespace, and this requires metadata management to locate files across servers to provide a consistent view to the clients. Let's look at the evolution of distributed file systems. Well, you might be familiar with one distributed file system. That's the Andrew file system, or AFS, that was developed right here at Carnegie Mellon. AFS is used by a number of organizations, and here you can see on screen a AFS tree example where we have multiple organizations that use AFS having individual subdirectories in AFS. Now, if you actually browse to /AFS, you should be able to see the complete AFS tree. So this is what we mean by clients being able to see a single global namespace. A further evolution of AFS was CODA. And then IBM developed a distributed file system that is quite popular for HPC applications known as GPFS, also PVFS, the parallel virtual file system. And then we have the Google file system, which we will be looking into in detail in this unit. So what are some of the design characteristics of distributed file systems? What are some of the design decisions that a person who creates a distributed file system needs to decide on? First, they need to consider factors such as performance. Scalability is a really important factor in DFS, especially with regards to the type of application you're using and how many anticipated users you might have for your DFS. Fault tolerance is another important design characteristic. Consistency as well, and sharing semantics. We'll just touch upon each of these one by one. So, performance and scalability. Performance is typically based on the target application's needs. So, depending on whether your DFS is used for database transactions or streaming data or batch jobs, you have to design the system with those performance requirements in mind. Scalability is also quite important in distributed file systems. So the most popular distributed file systems also tend to be some of the most scalable ones. So well-designed systems that can scale to thousands or hundreds of thousands of simultaneous users tend to do well in the DFS space. And this requires a engineering effort from the design of the distributed system itself, so that you are able to sort of distribute the work among all of the nodes that are involved in the distributed file system. So basically, being able to support a large number of concurrent users and clients brings about some other issues when it comes to design. You have to worry about the safety of operations, what happens when multiple people access the same resource at the same time. The question is, do you want to allow it? And if you do allow it, how do you try to keep things consistent, so to speak? So we'll look at that as well. Another key feature in distributed file systems is the idea of fault tolerance. Once you have files spread across multiple file servers, if you remember our talk on failure, the more pieces you have to your complex system, the probability of a single component failing and bringing the system down will actually increase. So fault tolerance is quite important in distributed file systems because a single localized failure could cause a failure in the global file system itself. So by design, you have to be careful. So if you lose one or more file servers, it's quite possible that you might lose data. So one of the major solutions for this is replication. You don't write data to just one server, you actually keep copies on multiple servers. So when you design a distributed file system, then these are some of the design decisions you have to make with regards to replication. Is at what level do you replicate? Do you replicate at files, blocks, or bytes? And if you do replicate, then how many replicas do you create, right? So Google's file system, for example, and Hadoop's HDFS have a typical replication factor of 3. That is, for every file block that they write in the distributed file system, they keep 3 copies of it. A big issue with replication is how do you keep replicas consistent? If your distributed file system allows you to write over blocks and you have multiple copies of those blocks, then, well, you can't have inconsistent versions of those blocks, because then some folks may read the old versions of the block. So how do you keep that consistent? That's a big question. This kind of boils down to, when do you report that an operation is complete to a client? So if you write to a single replica, do you go back to the client and say, hey, I'm done writing, and then you replicate that block in the background? Or do you wait for all the replicas to be written out before you report to the client? This is obviously a trade-off with performance. So in distributed file systems, it's quite possible that a distributed file system has multiple copies of data. Another aspect of distributed file systems is they could cache the data. So clients could possibly cache file blocks. And that's in fact what AFS does, is that whenever you request a single file on AFS, it will copy that entire file down to your machine, the client, and basically you work on that local copy. And then if you have any changes, you write it back. So you basically have a whole file cache in your local machine. And as we saw in the previous slide, you could also replicate data for fault tolerance reasons. If you have multiple copies of data, then you run into a consistency problem. So what type of consistency model do you want your distributed system, especially this distributed file system, to support? You could have strong or eventual consistency. Those are the sort of the kind of the two extremes of consistencies. There are multiple consistency models, and we will be covering them in detail as we go through the unit. So in strong consistency, you can sort of ensure to clients that they will always get the freshest copy of data, but there's a cost involved, obviously, right? So you can't ensure that a copy of some kind of data in your distributed file system is fresh unless you actually go and read from all the replicas and then compare them and then return back the freshest data to the client. So there is a performance cost involved. In eventual consistency, you might be able to just say to clients that, hey, here's a copy of the data. I can't guarantee that it's fresh, but for certain applications, that's okay, where they don't mind trading consistency for performance. So eventual consistency is fast, but the data could be stale. This brings us to the idea of file sharing semantics in distributed file systems. The semantics of file sharing sort of dictate to the applications and the clients that this is the expected behavior of the distributed file system, and application programmers should write their programs accordingly, and users of the system also should use the systems accordingly. So Unix or POSIX semantics is the standard file system semantics that we are all used to in the standard Unix file system. In this sort of semantic, it's a very strict semantic in the sense that if you write a single byte to a file, that update should be immediately visible to all clients. Obviously, this is something that's quite difficult to achieve, and there is a performance cost involved with this, because you have to have this complicated mechanism to be able to ensure this. In session semantics, file updates are typically visible at the end of a session. So AFS is an example of a distributed file system that uses session semantics. So a typical session spans the opening of a file and the closing of a file. So typically AFS will only make all the updates visible after the file has been closed by the clients. And then there's the idea of immutable semantics. That is, files that have been written once can never ever be opened later for writes. And in fact, distributed file systems such as GFS or Google File System actually use immutable semantics. So, some other distributed file systems may have immutable semantics in the form of versioning, such that, current data is never overwritten. You always write a newer version of the file, for example, right? Some file systems allow for transactional semantics. That is, it allows for additional information to be passed onto the file system, similar to a database transaction. So you can actually say that, okay, this is where I'm going to start a transaction on the file system, and you perform a bunch of operations, and then you have a commit part of the transaction. So anything between the start and the commit will either happen entirely or will not happen at all. That is, it'll roll back. So that's the idea of transactional semantics in distributed file systems.